Alright, hello everyone. I think this is going to be a super long video because I haven't really planned out what I'm going to do here. But my goal is to go over 4 papers here which I've downloaded which are interesting to me. I'm going to read out the abstract. I've done a video similar to this, but if I read every single word of each and all of these articles here, this video is going to be like 4 hours, which, it's not too bad, but I don't want to make it too long. I kind of want to just get a broad overview of everything that I'm looking at here. And hopefully you learn something new, and hopefully it's interesting to you. So all of these papers are related to batteries, specifically lithium metal batteries. We got lithium metal anodes over here. And they're separated by the material they use. So this one here is titled Synergistic Effect of Lithiophilic Zinc Nanoparticles and N-Doped for Stable Lithium Metal Anodes. So my main interest here was this zinc. I searched up for the word lithiophilic and I searched up zinc nanoparticles, and this is the article that came up that was interesting to me. So zinc nanoparticles are interesting, and it turns out that they are lithiophilic. What does this mean? If you've heard of like arachnophobia, like fear of spiders, if there's arachnophilia, there is like love for spiders or like affinity for spiders. So this thing here is kind of similar. You have lithiophilic zinc nanoparticles, which means that the lithium is attracted to the zinc. There could be also lithophobic materials which don't like lithium. And my interest here is that, these nanoparticles are attracted to lithium, so they can kind of help in certain parts of the battery if the battery uses lithium metal. We got the same kind of concept for tin. So we have another article here titled Guided Lithium Nucleation and Growth on Lithiophilic Tin Decorated Copper Substrate. So here the material of interest is tin, which was different from the zinc in this article. Then here we have lithiophilic silver nanoparticle layer on copper current collector towards stable lithium metal anode. So the material of interest here is silver. And the last paper we have is laser generated gold nanoparticles as lithophilic sites in self-supported film host for anode-free lithium metal battery. So I'm going to go through all of these papers. I'm going to read the abstract. I'm going to sweep through some of the pictures, and I'm going to read the conclusion and just kind of get a broad overview. Maybe I'll highlight some things. Maybe I'll just note stuff in my mind. But this is, I guess, like a 7-minute summary of scientific articles. It's not going to be 7 minutes. It's just going to be a quick overview of each of them. So let's start with the gold one. Let's move to the silver next. Let's go tin after that, and let's do zinc at the end. So get some snacks, get some popcorn, get some water. I got some water over here. I'm going to take a sip before I read this and just take a look at the abstract. So here we have a graphical abstract, but we also have the standard abstract. I'm going to read the standard abstract first. Anode-free lithium metal batteries, AFLMBs, anode-free lithium metal batteries, are considered to have greater application potential than traditional lithium metal batteries because of their higher energy density and safety. Unfortunately, their poor cycling performances originated from the unsatisfactory reversibility of lithium plating slash stripping remains a big challenge. A rational designed host for lithium deposition is an effective solving strategy. Herein, pure gold nanoparticles, NPs, without any impurities, are prepared by a liquid phase laser irradiation technology to construct and develop a self-supported gold reduced graphene oxide, AU/reduced graphene oxide, gold on reduced graphene oxide film as lithium deposition host for anode-free lithium metal batteries. The densely and uniformly distributed gold NPs provide abundant lithophilic sites that significantly reduce the nucleation barrier of lithium, attributed to the precise regulation of gold sites towards lithium nucleation/growth. Dendrites free anode and improved electrical chemical performance are obtained by using the gold/reduced graphene oxide film host. It keeps stable for 30 minutes of lithiation at 6 milliamps per centimeter squared without dendrite formation. Additionally, the lithium/gold graphene oxide half cells showed an overpotential close to 0 millivolts and maintains a Coulombic efficiency exceeding 97% after 500 cycles at 1 milliamp per centimeter squared. Moreover, A symmetric gold slash reduced graphene oxide lithium cell can operate for 700 hours without short circuit. When paired with lithium iron phosphate, I think, LFP, to assemble a full battery, the gold slash reduced graphene oxide lithium achieves 96% capacity retention after 100 cycles. Interesting. I don't know if any of that meant anything to you guys. You'll read a lot of these things when you read battery articles, but also there's some interesting stuff like this graphene oxide here, the laser irradiation technology they use to develop the nanoparticles. What is interesting to me, I don't know. We'll take a look. Let's take a look at this graphical abstract. A self-supported gold slash reduced graphene oxide film as a lithium deposition host is developed by employing the liquid phase laser generated gold nanoparticles as lithiophilic sites, attributed to the precise regulation of gold sites towards lithium nucleation slash growth. Dendrite-free anode and improved electrochemical performance are obtained by using the gold slash reduced graphene oxide film. So personally, for me, I'm interested in how they develop this film, and then how they develop the batteries that use this film, and then how they test these batteries. So you can see here, actually, let's zoom in to the abstract. We got ethanol solvent, laser beam, gold foil, gold nanoparticles. So you have gold foil, it's chilling in some solvent, and you slam it with a laser. The laser like shoots off little gold nanoparticles, and this is how they fabricate them. Then they take reduced graphene oxide, which I'm assuming is these kind of layers, these kind of like sheets over here, looks like fabric, and you have the gold nanoparticles on top of that, and they show you this thing over here. Then we have lithium deposition. So I'm assuming this lithium is the blue, little blue dots, and you can see lithium nucleation. Nucleation basically means the lithium attracts onto the gold because the gold is lithiophilic. It has an affinity for lithium, and then the lithium slightly grows. And you can see the lithium grows uniformly over this entire matrix here. Then over here, what we got is potential in millivolts as a function of capacity. And we got two curves, the red and the blue one. The blue one is the reduced graphene oxide. So you can see it has, over the span of capacity, it has a lower potential. I don't know. And then the reduced graphene oxide with the gold nanoparticles over here is a bit lower. I'm not sure what that means. Just a graph over here. And then here they show you potential as a function of time. We got the reduced graphene oxide, lithium, which is not this material that they made. It's just a reduced graphene oxide with lithium, no nanoparticles on it. Then we got the gold slash reduced graphene oxide lithium, which is this red. And you can see the voltage here, it continues for more than 700 hours. Meanwhile, the blue one dies off over here after 100 hours. So it looks like their battery lasted much longer, about 7 times longer, with this gold matrix thing that they developed here. I don't know if that's the case. Let's zoom through. Let's not read too much. We're going to just look at the main section. So introduction, normally this gives you like a foundation of what's happening. Lithium metal batteries are considered to be active, whatever. And you could read everything about that. So this is one paragraph about like lithium metal batteries. Let's see. For an anode-free lithium metal battery, so they talk about that. Then we have here, in recent years, due to development of nanotechnology, the strategy of introducing heterogeneous crystal species in the host structure has been proposed. So they say that herein, when they say, they're talking about what we're doing in this article specifically. We meaning like the team of authors, these guys here, from their university. So let's just read that very quickly. It says, liquid laser irradiation technology was developed to obtain purified gold nanoparticles, possessing the advantage of controllable particle size, good dispersion, high yield, adjustable concentration, and absence of ligands, whatever. The gold nanoparticles were applied to decorate reduced graphene oxide nanosheets, forming a self-supported film host for lithium deposition. Such a rational design not only can endow the stable and sustainable lithophilicity of film host, but also maximize the use of the advantages of the graphene sheets. So this graphene oxide has its own interests that I'm not experienced in, but it's something that I'm kind of just taking note in. The constructed film host is effective from the initial nucleation stage of lithium, and the gold lithophilic sites decorated on the graphene guide uniform lithium deposition, ensuring homogeneous lithium nucleation. Additionally, the good flexibility of the film structure allows the host to accommodate volume changes during the reduplicative charge and discharge process. This study demonstrates that the dendrite suppression can be achieved through the rational design of lithium metal deposition hosts, which is of great significance for realizing high performance lithium metal batteries. Very cool, very interesting. You guys can read this if you want. Let's take a look at this. So number one, introduction. Number two, material and methods. Material. So here they explain how they fabricate the graphene oxide and the nanoparticles, preparation of the gold nanoparticles, preparation of the gold reduced graphene oxide film, materials characterization. This is a super interesting category. They use a bunch of different analysis techniques to see if what they're making is actually like accurate to what they theorize. So they have a couple machines here that they're going to use. They also have electrical chemical tests, which are interesting to me. Let's just take a look at this. To test the electrochemical performance, a CR 2025 coin cell was assembled in an argon-filled glove box. The coulombic efficiency and overpotential of the batteries were measured in lithium copper half cells. Okay, I'm not going to read too much of that, but they tell you some information here. I got an interesting picture here. This picture looks similar to the abstract that we had before. Let's see here. They start with this, creating the nanoparticles using this laser irradiation thing. Mix with reduced graphene oxide. It looks like they have a little jar here with a solution. Inside the solution, you have the reduced graphene oxide sheets. You put the sheets in there, you put the nanoparticles in there. Boom. Vacuum filtration, I'm not sure what that means. And then you get these nice uniform sheets of the structure here. 3D kind of structure, matrix is what I call it, and a lot of people call it, of the material. And this is what they think it looks like. Does it actually look like this? Who knows? This is, I think, a graphical 3D computer generated illustration of this. I'm not sure if that's exactly what ended up happening, but that's why this kind of experimental section exists, so they can confirm if they actually developed this. So let's take a look at the next section, results and discussion, design principle and material characterization. So they characterize the materials a bit further. They got some interesting pictures here. Let's actually read this. A and B, which is here and here. SEM images of gold on reduced graphene oxide. TEM images of reduced graphene oxide and gold graphene oxide. Here. Respectively. E. HAADF STEM images of gold on reduced graphene oxide and corresponding mappings of gold, oxygen, copper, carbon. Interesting. So I'm not sure what to make of that yet. XRD patterns of the reduced graphene oxide and gold reduced graphene oxide. XPS, survey of spectra, high resolution XPS. Okay, so some interesting characterization stuff. Let's move on. Regulation of lithium deposition. Interesting category. I'm not going to read through that too much. And we got this. This looks like interesting electrochemical results. So let's read them together. We got A and B, the relationship between overpotential of gold reduced graphene oxide electrode and gold content at 0.2 milliamp per centimeter squared. So this graph here, potential as a function of capacity, and this is called the overpotential, right? A and B. A and B over here. Overpotential, potential, and here they give you a bar chart as a function of gold percentage. So gold percentage over here, you get a lot of voltage over potential in millivolts, 16.4 millivolts, 13% gold, this much, 19% gold, it drops, 26% gold, it rises a bit, but 32% gold, you get the lowest amount, 0.7 millivolts. I don't know, that might be kind of interesting, that might be kind of useful. Not too sure what to make of that yet. C, overpotential comparison of reduced graphene oxide and gold reduced graphene oxide electrodes at one current density. So we saw this earlier. I'm not too sure what to make of this as well, but they're basically comparing the reduced graphene oxide, which is basically these sheets over here with no gold nanoparticles. So just those sheets inside the coin cell. And over here, they're comparing it with the gold reduced graphene oxide. Interesting. Overpotential change. This is D. Let's actually take a look at D. Overpotential change of reduced graphene oxide and gold reduced graphene oxide electrodes at different current densities. Let's take a look at this. So we got potential here in millivolts as a function of time. The red function is the gold with the reduced graphene oxide. The blue function is just the reduced graphene oxide. And over here, I guess they have different current densities. 0.1 milliamps per centimeter squared, 1, 2, 3, 4, and 5 milliamps per centimeter squared. So what can I see here? I mean, it looks like these ones kind of look the same, but over here you can see the red is actually a bit lower in voltage than the blue. You can see it's closer to 0. Imagine 0 here is on the axis right here. This is the 0 line. So if you have this, we have over here at 1 milliamp per centimeter squared. The red function, which is the gold reduced graphene oxide, is a bit lower in potential, both on the positive potential and negative potential side. But the reduced graphene oxide is a bit higher. So I don't know if this is useful. I don't know what this is showing you, but it's cool that they included it here. Let's read again over here. E coulombic efficiency of both of these. I'm not gonna say reduced graphene oxide, gold reduced graphene oxide. You guys know that they're comparing both of them now at this current density with area capacity of this. So that is part E. So cycle number, you could see cycle number about 150. This blue function, this blue scatter plot ends. It dies off here. So it looks like this cell with the reduced graphene oxide dies, and this gold reduced graphene oxide one continues all the way to like 600 cycles. And they both look like they have the same amount of coulombic efficiency, about 100%. Interesting. F voltage curves of the reduced graphene oxide lithium and this gold reduced graphene oxide lithium symmetric cells. Okay, so we saw this earlier. I'm not going to speak about that again. And then we have EIS, which are electrochemical impedance spectroscopy curves for both of them. So they give you this. I'm not too sure how to read these, but it's cool they included it here. So a bunch of interesting data they include. Let's keep reading through the paper. Let's zoom out a little bit. Electrochemical performance of lithium metal batteries. We get some other plots here. It looks like they're comparing kind of similar things, the red and the blue. But here they're making full cells. So before they had like, I guess, half cells or symmetric cells. Here they have full cells. If you don't know the difference between those two, don't stress. We're going to just zoom in through a paper over here. Cool. Nucleation mechanism of lithium. This is pretty interesting. They're talking about the mechanism, like what they think is happening here. And they actually show you a cool little picture. So reduced graphene oxide, no gold nanoparticles. You can see the gold nanoparticles over here. Nucleation, so the lithium deposits. And then here we have the lithium dendrites, which are these spiky icicle things made of lithium, which are bad. They cause short circuits and explosions in batteries, so you don't want that. But if you add the gold, you can see the lithium is attracted to the gold, and it nicely starts coating the gold nanoparticle. And instead of forming these jagged structures, they form these nice little bubbles all throughout the graphene oxide 3D structure. So I think that's what it says here. We got SEM. So you can see the dendrites over here are actually visible in the SEM. These little tiny like bubbles and stuff. 0 minutes, 1 minute, 10 minutes, 20 minutes, 30 minutes. At 30 minutes, you have these like little spikes over here, which are not good. They actually tell you these are the lithium dendrites right here. And over here, you don't see anything forming dendrite free. So it actually looks like what they are saying is happening is actually happening. Very cool. And then the conclusion. Let's see how big the conclusion is. Look at some more figures over here. Morphology and structure of reduced graphene oxide here and silver on reduced graphene oxide here after lithium deposition. So you can see here there's a bunch of little dots and stuff. Here it looks a bit more uniform. We got intensity binding energy. We got intensity binding energy again, intensity, some more kind of XPS, SEM, XRD kind of analysis. I'm not going to look at that too much. But it looks like the conclusion is just this over here with this last sentence over here, and then the article ends. So let's read the conclusion. In summary, pure gold nanoparticles without any impurities were prepared by a liquid phase laser irradiation technology and then employed to construct a freestanding gold reduced graphene oxide film host for lithium deposition. The dense and uniformly distributed gold NPs provide abundant active sites that significantly reduce the nucleation barrier of lithium metal, almost eliminating the required overpotential for nucleation. Attributed to the precise regulation of gold sites towards lithium nucleation/growth, improved electrochemical performance obtained by using the gold reduced graphene oxide film as a lithium metal free anode for lithium metal batteries. Compared to those decorated with functional groups and atom doping, the gold/reduced graphene oxide film host shows a long-term reversible induced directional deposition while reducing side reactions, which not only significantly inhibits the dendrite growth, but also enhances the long-term cycle life of both half cells, symmetric cells, and full cells across the board. This work provides a unique strategy to the safety concerns associated with lithium metal battery anodes, which is significant for practical application in high energy density batteries. Awesome, amazing. Credit authorship contribution statement. All of these guys over here. Let's take a look at the top of the article. Here's the article title. Here are the authors, and there's some information from where they're coming from. So thank you very much, authors, for writing this. Super interesting. I'm going to read it on my own time, a bit more in depth, and see how it looks. So that's the gold. Now that took a hot minute, but you know what? I think I'm going to crush through it. We're going to go through all of these. Let's go with the silver. Let's see how long this article is. This article has 7 pages. This last one was 10 pages. The tin one is 8 pages. And the zinc one is 9 pages. So not too bad. We're going to go through the same thing for this one. Lithiophilic silver nanoparticle layer on copper current collector toward stable lithium metal anode. Here are the authors. Here is the institution that they're working with. Thank you again very much. We got some supporting information over here. You can click in and take a look at some more stuff that they published related to this article. Let's read the abstract here. Intractable hurdles of low coulombic efficiency and dendritic lithium formation during a repeated deposition/stripping process hinder the commercial use of lithium metal anode for next generation battery systems. Achieving uniform lithium nucleation is one of the effective strategies to address these issues, and it is of practical importance to realize this on a commercial copper current collector that is lithophobic. Cool. Herein, we design a nanostructured silver lithophilic layer on a copper foil via an electroless plating process for a lithium metal current collector. The deposition of the lithophilic silver nanoparticles that are homogeneously distributed on the copper foil can reduce the nucleation over potential, realizing uniform lithium nucleation and subsequently flat lithium plating. As a result, a stable cycle stability of up to 360 hours at 1 milliamp per centimeter squared, and an average coulombic efficiency of 94.5% for 100 cycles, 1 milliamp per centimeter squared, are achieved. Furthermore, copper silver full cells with lithium iron phosphate, LFP, as a cathode exhibit good cycle performances and low polarization voltage. This approach provides another facile way for a stable lithium metal anode. And here are some keywords. Okay, interesting. So we got some pictures here. I think I'm going to zoom through this paper a bit quicker just to see what they did. Like before, we saw that they had reduced graphene oxide sheets, and they had the gold nanoparticles kind of embedded in there, and they had that like chilling somewhere in the battery. I didn't see the construction of the battery in depth, but I want to see like kind of what differences this article has from the other one, other than just the material difference. So you can see here we have silver. Before we had some other material like gold. So let's zoom through again. Introduction, you can read this if you wish. Electroless plating. Chemical silver plating solution, copper foil. Then we got some XRD graphs here. Schematic of the fabrication of the copper silver sample from a commercial copper foil, and typical images of the bare copper foil and the copper silver sample are shown in the upper section. So bare copper with the silver added on it. XRD spectra. The bare copper foil and copper silver samples synthesized via electroless plating. SEM images. So these SEM images are here. Let's see here. So we got the bare copper foil. So copper is super jagged and stuff. Then we have D, 1 minute. I guess 1 minute of this plating process. You see this, and I suppose these little dots over here on top of the copper are the silver. Then we have 1.5 minutes, more silver, and 2 minutes, much more silver. The scale bars represent 1 micrometer. Cool. Okay, the main thing I'm going to look at here is the experimental section, fabrication of copper-silver current collectors. Let's read this in depth. First, one piece of commercial copper foil, 18 micrometer in thickness, was cleaned in ethanol and acetone with ultrasonication. After drying, it was immersed in the chemical plating solution containing both silver plating and reduced reducing solutions at a volume ratio of 1 to 1 at room temperature for different reaction times, 1, 1.5, 2, and 3 minutes, separately. The obtained samples are denoted as copper, silver, -X, where X represents the reaction time, which is 1, 1.5, 2, or 3 minutes. The silver plating solution was prepared by adding ammonia, which is NH3 with the H2O over there, into 10 milliliters of silver nitrate, AgNO3, solution at this concentration over here until it turned into a transparent, and then 10 milliliters of sodium hydroxide, salt, I assume, solution at this concentration was mixed with the reaction solution. Finally, ammonia was slowly added into the solution until it became limpid. Not sure what this word means. Can we define this? Define. Oh my god. We're not going to define limpid right now. For the preparation of reducing solution, 45 grams of glucose and tartic acid, 100 milliliters of ethanol were dissolved into 1,000 milliliters deionized water. After being washed with deionized water and alcohol for some times, the samples were dried under vacuum 60 degrees Celsius for 12 hours. The copper silver foils were cut into circular discs with a diameter of 1.6 centimeters as a current collector for further coin cell assembly. Interesting. Looks like very kind of complicated chemical reaction here with glucose and random other shit happening. Interesting. Very, very cool. I'm just going to keep this in my mind, but I'm not going to look at it too much. I'm just going to zoom through the rest of the paper here. So we got, again, characterization with different machines and stuff to see if their material is actually doing this stuff. This is a bit of the characterization. They did some characterization here as well. Super interesting. Not going to look at it too much for this video. And then electrochemical measurements, which is how they, what they do. So let's actually read this a little bit too. I didn't read it in the other article, but this is where they talk about how they make the coin cell. So we have a CR2032 coin cell assembled with cell guard separators using the copper, silver, or copper current collector. So they made two types of coin cells, one with their fabricated material and one with just the copper. And lithium foil as the counter reference electrode. Then they have LiTFSI as the electrolyte, I'm assuming, with some additives. Electrolyte, unless otherwise specified, electrolyte was employed in each coin cell. These coin cells were tested on a Newware battery testing system. To evaluate the coulombic efficiency, the current collector was first deposited with 1 milliamp hour per centimeter squared and lithium, and then stripped to a cutoff voltage of 0.5 volts. Interesting. So this is interesting. I'm going to look at this a bit more on my own time, but right now I'm just kind of interested in what pictures they have here. So yeah, it looks good. I'm not going to look at this too much as well. This is the results section. Let's take a look at this. SEM images of A, bare copper foil, B, copper with the silver nanoparticles, 1.5 minutes sample. So you can see it looks very, very different. Why does it look different? I don't know. Samples after 150 cycles. So this is after they cycle the battery, they look at the copper and they see this, and they look at the copper with the silver added onto it, and it looks like this. Voltage time curves of lithium anode deposition, stripping of the bare copper foil and the copper with the silver nanoparticles at 1.5 minutes. Sample with the cycling capacities of C, 1 milliamp hour per centimeter squared. Boom. So we have voltage as a function of time. Here we have the black. You could see boom here, it like spikes up, higher voltage, and then it looks like it dies off over here. I'm not too sure. I can't confirm that. And then this blue one continues for 400 hours. And this is at a specific current density over here. So we have also D over here at another current density. And you could see it kind of continues, but the black function here with just the copper looks like it reaches higher voltages and it's a bit more jagged. The blue one looks like it's constant, uniform throughout the whole process. Pretty interesting. Then over here we got E, which is coulombic efficiency of the copper foil and the copper silver. Sample with an arrow capacity of this at 1 milliamp per centimeter squared using blank. Cool. So we have coulombic efficiency. It looks like continues. Both of them look like they're 100, but then the copper one just drops off over here. Boom. And then it kind of like jumps around a lot. Kind of crazy stuff happens. Meanwhile, so that happens at around cycle number 20. maybe at 20 it starts falling off. Meanwhile, the copper with the silver on it continues on until cycle 40 about. Then it drops off a bunch, raises a bit, and also does some crazy stuff. So very interesting. Maybe this initial section right here is pretty interesting. I don't know what's happening over here at the end. It looks kind of crazy to me. And then here we have another EIS graph. Not sure how I can analyze the EIS graphs at the current time. But okay, it looks pretty cool to me. We're going to zoom through. Cycling performance of the lithium, copper, and lithium iron phosphate. So this is the full cell, which is, I think, the one in black. And then the lithium copper with the silver, which is the one in blue, full cell. So full cell is just like the anode and the cathode are different. The ones that they developed here, I'm not sure if those are full cells. They're probably not full cells. They're something else. So interesting. So we got some cycle number as a function of specific capacity. Looks like the blue one has a higher specific capacity throughout all 200 cycles. Then here we have a cycle number at a different C rate, which is a different current for each of these. So it looks like the blue one is outperforming the black one for each of these by just a little bit of specific capacity here. Looks interesting. Okay, and that's about it. So pretty cool, kind of quick zoom through. Very interesting stuff. I would like to spend more time on it, but I don't want to post this on a 4-hour long video, so just a quick zoom through of everything here. Let's take a look at the conclusion. A commercial copper foil with lithiophilic silver nanoparticles coating was fabricated as the lithium metal current collector by a facile, low-cost, and scalable electrolysis plating approach. These homogeneously distributed silver nanoparticles can alloy with lithium to form lithiophilic layer and are thus beneficial to reduce the nucleation over potential and to guide lithium uniform nucleation and deposition. The initial homogeneous deposition further regulates the following lithium growth/stripping process, and thus a stable interface is realized with dendrite-free morphology. As a result, the copper-silver 1.5 minute sample anode exhibits an improved lifespan of up to 360 hours at this current density, which is more than 2 times that of the commercial copper foil at 130 hours. Cool. Furthermore, this copper-silver 1.5 minute current collector also exhibits a high coulombic efficiency with an average value of 94.5% for 100 cycles at this current density. In addition, a much improved cycling performance is also obtained for the full cell. Astounding, fantastic work. Thank you very much, authors, for writing this. I appreciate it. Good looking out. Let's take a look at the tin one. Tin one's a bit longer. Let me just zoom through it like overall like this to see if there's anything interesting. Hold up. Cool. Nice little diagram over here. Images, some CV curves, not as unique compared to the other two papers. The other two papers didn't look like they had some CV curves on it. Ooh, some nice little like chemical structures here. Also pretty unique. Some pretty similar looking graphs to the other ones, some battery experiments, and then the conclusion. You know what, for this one, let's read the conclusion first. Conclusion. In summary, we constructed an ultra-thin SN, here means tin, layer decorated with SN copper current collector by a simple electrolysis tin plating method. Electrolysis is the same thing that the previous article used. The tin decorated layer is composed of about 100 nanometer sized primary particles, and its thickness is optimized to 1 micrometer, which is capable of withstanding the mechanical strain of the lithium tin alloying reaction and remains functional during the repeated lithium plating/stripping cycles. The lithiophilic tin layer not only lowers the lithium nucleation over potential, but also promotes the fast lithium deposition kinetics. These two aspects cooperate to bring about uniform lithium deposition. Thus, large granular and dendrite-free lithium deposit was obtained. First principle calculations indicate the lithophilic nature of the SN decorated, tin decorated layer originated from the weak absorption energy and fast self-diffusion rate of lithium atoms in lithium tin alloy surface. As a result, the tin copper electrode demonstrates superior electrochemical performance for lithium plating slash stripping. The lithium tin copper half cells show a higher average Coulombic efficiency, 98.9%, and improved cycle life for 250 cycles. The lithium tin copper symmetric cell offers stable cycling for over 1200 hours with small polarization of 18 millivolts and one at this current density and this specific capacity density. Moreover, lithium metal full cell using commercial LFP cathode sheet exhibits enhanced cycling stability for over 300 cycles at a high areal capacity of 1.8 milliamp hours per centimeter squared. Our results provide an effective method to regulate the lithium deposition behavior, and the underlying mechanism can be applicable to various lithophilic heterogeneous metal modification layers for enabling dendrite-free lithium metal anode. Okay, interesting. So I don't want to make this video too long, so I might just look at that for this article. Thank you guys for writing it. I'm going to take a look at it a bit more in depth. This is published 2022. What I'm interested in, though, is how they fabricate their coin cells. So, experimental materials. Here they have materials. Preparation of tin plating bath. So this, I'm assuming, similar to the other paper we read. 1.354 grams of stannous chloride dihydride. This many grams of this, and this many grams of that, and this many grams of this many grams of HCl were weighed respectively. These reagents were dissolved in 60 mL of deionized water at 50 degrees Celsius, stirred until mixed well. The obtained tin plating bath was then used for further experiments. Preparation of the electrode. The electrolyte tin plating on the copper substrate was realized via a simple one-step chemical substitution reaction, specifically after washing with acetone. Okay, structure and morphology, again, characterization. Electrochemical measurements. This is what I'm interested in. The electrochemical measurements were done with a CR 2016 type coin cell assembled in an argon-filled glove box with cell guard separator. The electrolytes were this. With these additives, the amount of electrolyte used in each cell was 50 microliters. Galvanostatic charge discharge performance was measured by this machine, multi-channel battery tester. Lithium/M, copper. M is equal to copper and the tin copper, so they kind of changed it. They got two different types of cell. Half cells were cycled at 0.51 and 2 milliamp current density. By plating lithium metal to a fixed capacity of 1 milliamp hour per centimeter squared, and stripped the cell to 0.2. Symmetric cells were tested galvanostatically. Okay. Full cells were assembled using this material that they made, which was plated at this specific capacity, lithium metal at a current density of this, lithium iron phosphate as a cathode, cyclic voltammograms. Okay, so I guess here they talk about how they fabricate the coin cells and how they test them. Very interesting. That is the tin article. Let's finalize here with the zinc article. Let's take a look at the zinc. Let's zoom through and kind of go through the same thing. So the authors here and where they are researching from. Very cool. Thank you guys for publishing this. 2021. Very cool. Let me enable scrolling here. Some keywords that are interesting, some introduction, and experimental. Preparation of zinc, NC, CC, NC, CC. So if we read the introduction and the abstract, we should know what this is, but I'm just going to look at the experimental section. Commercial carbon cloth was first cleaned by concentrated hydrochloric acid and then washed with distilled water. Subsequently, the treated CC, which is the carbon cloth, dried at 60 Celsius, cut into pieces this amount, and immersed in PVP solution. Ultrasonic treatment for 40 minutes was then mixed with this and this. Meanwhile, at 1.19 grams zinc nitrate hexahydride, dissolved in methanol, was slowly added to the former solution under stirring for 30 minutes. After aged at room temperature for 24 hours, the ZIF This is the problem when you kind of just jump into an article and don't read the abstract. Was abstained after washing. Okay. Hiding. Okay, interesting. So I'm kind of going through this a bit quick because my brain kind of hurts a bit. So I kind of want to take a break, but I don't want to take a break before finishing this video and just zooming through all these 4 articles. Okay, preparation of zinc and carbon cloth. So we got this amount of this, sodium hydroxide dissolved in this, immersed, stirred, subsequently transferred to 100 mils of this, autoclave 160 degrees, 20 hours. Cool. Material characterization, again, some interesting material characterization. Not going to read that right now. Let's take a look at the electrochemical measurements. So we got this fabricated material here with the zinc, with the NC, and the NC with the carbon cloth, and the zinc with the carbon cloth, and just the carbon cloth. So we got the carbon cloth, we got the zinc with the carbon cloth, the NC with the carbon cloth, I don't know what this NC is, and the zinc with the NC with the carbon cloth. So 4 different materials here. Composites were cut into discs with a diameter of 11 millimeters, and then adopted as the working electrode to assemble coin cells in an argon-filled glove box for electrochemical testing. The thickness of these discs were controlled to approximately 250 micrometers. For symmetric cell testing, lithium was firstly deposited with a capacity of this onto this, and this, all the 4 materials respectively, current densities of this to form that. Interesting. Lithium was deposited onto those. Okay, the thickness of these electrodes was approximately 270 micrometers. So from 250 to 270. The cycling performance of these symmetric cells was tested at various current densities of these. CellGuard was used as a separator. Electrolyte is this in a mixture of that with these additives. Full cells were assembled using the classic cathode that was used in the other papers. They give some more information about that. On high mass loading, controlled to be this. And bare lithium electrodes were used as anodes. The negative positive electrode capacity ratio is controlled to be approximately 28. The mass loading, okay. Thickness of bare lithium anode adopted in half cell and symmetric cells was approximately this. Okay, so I'm zooming through this. Ooh, computational method. This is something unique that was not included in the other paper, so I'm just going to read it. Density functional theory calculations were carried out using projector augmented wave PAW method as implemented in Vienna AB Initio. Okay. A generalized gradient approximation of this functional was employed to describe the exchange correlation. An energy cutoff of 500 electron volts and gamma centered 5 times 5 points mesh was applied to all calculations. The structures relaxed until the forces and total energy on all the atoms were converged to less than this. The zinc and lithium slab models were the cleaved surface of each metal with the lowest surface energy, and the 4-layered supercell with 20A vacuum was adopted to evaluate the interaction between lithium and electrode. The binding energy EB was calculated as follows, where E sub, okay, interesting. So they got some DFT calculations here, which I'm assuming they're going to show in a little bit. Results and discussion. Let's zoom through. Okay. We got this material here. This is the carbon cloth. I'm assuming they're pulling out 1 fiber of this carbon cloth. Then we got the zinc plating. See, the zinc is coated on each of these things, which creates the ZIF 8cc, so the zinc onto this carbon cloth. Carbonization creates this thing with the NC, so I'm assuming this NC is the carbonization. And then we got the lithium plating onto this. Interesting. So then they got some more pictures, I'm assuming SEM images, and here we got some other interesting images that show you where the zinc, nitrogen, and carbon is. Pretty interesting. We got some images of what the actual thing looks like. We got some more SEM images. Very cool. Ah, this is probably the DFT. The summary of calculated binding energies between lithium and various substrates. The optimized absorption configuration of lithium on B, zinc, with this surface. So where is B? Here? Not too sure how to read this. C, lithium, here. Defect-free graphene, or graphite. Graphite N, over here. Pyridinic N, here. Okay, so a bunch of DFT calculations. Kind of interesting. And here they give you the binding energy. So here we got binding energy of lithium, looks like it's the lowest. Zinc, a bit higher. Graphite or graphene up here. Graphite or graphene with the zinc is more negative. Okay, so I'm assuming that, sorry, I kind of made a mistake. This is 0, and here the energy goes down into the negatives. Not sure how to read this, but here we got GNGR, which is the lowest one over here. So I'm assuming that's kind of interesting. Or maybe the highest kind of negative energy here is the most interesting. I'm not too sure. Here we got the classic battery cell experiments. So we can see the red one, which is lithium, zinc, NCCC, lasts the longest. The lithium with the NC without the zinc lasts over here. The lithium with just the CC, the carbon cloth, lasts here, and just the lithium dies here. So very interesting. They kind of show you the differences here. With the zinc, it lasts the longest. Okay, let's zoom through. We got some Coulombic efficiency plots. As you can see, the red one, the lithium with the zinc with the NC here and the carbon cloth lasts the longest. 100 cycles. The other ones kind of die off. Their Coulombic efficiency drops off quite a lot. Same thing here. I'm assuming this is for different current densities and stuff like that. And what do we have here? Voltage as a function of capacity. Cool. And then we got this graph here, which is classic, which I have not been able to read. Okay, we're going to zoom through. We're going to read the conclusion. In this work, a novel zinc at NC at carbon cloth host has been synthesized for designing dendrite-free lithium metal anode. Owing to the synergistic role of zinc nanoparticles and N-doping inside the porous carbon polyhydrine, improving the absorption capacity of lithium, uniform lithium deposition along the carbon fibers of carbon cloth could be realized with the complete suppression of lithium dendrites. In addition, the uniform distribution of porous N-doped carbon polyhydride and on carbon cloth with high mechanical strength could effectively accommodate the volume change of the electrode upon a repeated lithium stripping/plating process, leading to the well-preserved structural integrity of the whole electrode and hence excellent long-term cycling stability. Consequently, the lithium zinc NCCC electrode exhibits a stable cycling performance for over 1200 hours at this current density without voltage fluctuations. When coupled with the full LFP cathode, a reverse capacity of this with capacity retention of 78% were achieved. The lithium zinc NCCC and LFP full cells at 1C after 200 cycles. This strategy opens up new strategies in the reasonable design of stable lithium metal anodes for high energy density lithium metal batteries. Okay, so I kind of zoomed very quickly through that last one. I kind of want to go get some tea. I wanted to do this without any cuts to show you kind of how I read through papers. Obviously, this is not what I would do if I'm like sitting down and actually trying to get info from this. I kind of just showed you like a little 7-minute summary. Get acquainted with the topics and read a little bit of some kind of different stuff related to lithium metal batteries with different materials that they use. So for this one, they got zinc with the carbon cloth on it. For this one, they got tin, kind of electrolysis plating. Same thing with this one, with the silver. And this one, they use kind of a laser strategy onto graphene oxide. So a bit of differences between each of the articles, but they're all pretty cool. They're all pretty interesting. I hope you learned something. Let me know if you have any questions about this or if you want to see more stuff like this. And peace out.